final piece to lesson 5.4 is going to be some mixed factoring practice where I'm just going to give you guys a polynomial and you're going to have to kind of go through your whole factoring flowchart to be able to figure out how to completely factor it. And then at the end, we're also going to do a little bit of an application, like where would you need to use the factoring stuff like this. So to get us started, for the first few problems, I'm not going to go through and factor every single one of them, but what I do want to do is, one, have you guys determine if there is or is not a GCF on it, and then two, with the remaining pieces that are left, I need you guys to determine which method you would be using to help you factor that particular polynomial. So I inserted over here the factoring flowchart that you guys had on your last set of notes. So remember, on the factoring flowchart, you always begin with the GCF. That will always come first. And then determine your method based off of how many terms you have. Do you have 2 terms left, 3 terms left, or 4 terms left? So if we take a look back over here on problem number 1, the first thing I want us to identify is there a GCF? And it looks like, based off of the previous lesson, maybe we needed a little more practice in identifying the greatest common factor, not just a common factor. So I've shown you guys a couple of different ways to do the GCF. If you're not being able to recognize a common factor and then recognize that you do not have the greatest common factor out of that, I would recommend doing the factor tree. So that's what I'm going to do first for this first one. Also, it's pretty big numbers, so I want to make sure that I get everything out of all 3 of those terms. So 20x to the third, we're going to do a factor tree for. So I know 20 could be 4 times 5. And then I'm just going to put x to the third here, and we'll break that down in just a second so I can save some room. 4, I know, would be 2 times 2. So we have 2 times 2. I would bring my 5 down. And then we know x cubed would be x times x times x. All right. Then I take a look at the negative 220x squared. I'm going to pull that one down over here a little bit. So negative 220x squared would be negative 1 times 220. We could do maybe 110 times 2 times that x squared, which we will break down in just a minute. All right, I'm going to bring my negative 1 straight down. 110 would be 55 times 2. And bring that 2 straight down. And bring your x squared straight down. And keep going. Negative 1, 55, I could do 11 times 5. Bring down my 2. Bring down my 2. And since all of those are now prime, in other words, they cannot break down any further, I'm going to go ahead and break down my x squared into x times x. So I've just broken those down into all of its prime factors. Again, we call that the prime factorization. Okay, 600, this big boy I'm going to come over here and do. So 600x, 600 we could do 60 times 10. 6 times 100, kind of whatever you see there, but we're going to have to break it down again anyway. So 60 would be 12 times 5. 10 would be 2 times 5. 12 I could break down into 3 times 4, but I know that 4 is 2 times 2, so I'm going to go ahead and break that one down a little bit further. Bring down my 5, bring down my 2, bring down my 2, and I definitely did not bring down my x all the way. So I can't forget that little guy. Okay, all of those, again, are prime. All of those are prime, all of those are prime. So in using the factor tree, what we're looking at is the bottom row of all the factor tree, of each factor tree. And we're going to circle what they have in common. So there's a 2, there's a 2, there's a 2. Okay, so they all have a 2 in common. So there's a 2. Oh, I was going to do this. Change colors. There's a 2. There's a 2. There's a 2. Okay, let's see what else. Oh, I see an x. They have an x. And there's an x, and there's an x. So the only way I can circle it is if all 3 of those highlighted lines has the same thing. So let's see, what else do they have? Oh, look, I do see another 2. Do they have anything else in common? I see a 5. Oh, yeah, they all have a 5 in common, too, huh? 5 and a 5 and a 5. So I see some X's here and an X here, but there's no more X's over here. So I'm not going to be able to circle any more X's. So it doesn't look like we have anything else in common between those two. So the stuff that is circled would be the GCF, right? That's what they have in common. It would be the greatest common factor. So 2 times 2 is 4, and 4 times 5 is 20, and then 20 times X. So my GCF for this one, sorry, there's not a lot of room there, is 20X. Okay, then I want to take a look at the stuff that's left over after we pull out that 20x, and that would be the stuff from each one of these lines that is not highlighted. So once we factor out or pull out the GCF, we're going to have 20x on the outside of the parentheses, and then on the inside we would have x times x, which is x squared, and it is positive. This one I have a negative 1 times an 11 times an x. We multiply all those together to get negative 11x. And then over here we have 3 times 2 times 2. So 2 times 2 is 4. 4 times 3 is positive 12 because there's not a negative on that one. So then after pulling out the GCF, we want to take a look at what is left here. And there are 3 terms here. So I'm going to come back over to the flow chart. We pulled out the GCF. Do we have 2 terms, 3 terms, or 4 terms? We have 3 terms. And it says a trinomial factoring strategy. The 2 that we used were the box method and grouping. Either one of those 2 methods will work just fine for you. So if I take a look at this one, and in both of those cases, we used the hopscotch squares to figure out the parts that we needed for the box and for grouping. So hopscotch squares definitely going to be used in either case. So if we take a look at this one, I'm going to try to break up the hopscotch square. I'm definitely going to zoom in here. So remember, the top box of the hopscotch square is the product, so x squared times 12, so 12x squared. The bottom box is the sum, which is the middle term of negative 11x. So then we're asking what times itself, what are the factors of 12x squared that would also add up to 11x? And then don't really have many options, just 12x and 1x, but then one of those needs to be negative. No? Let's think about that for a second. So if I make this guy negative, well, that would give me a positive 11x, so that's not going to work. Okay, what if I make this guy negative? Well, that would give me a negative 11x. Oh, I like that. But it does not give me a positive 12x squared. It would actually give me a negative 12x squared. So is there anything else that we could multiply factors of 12 that we can multiply together that would also give me a negative 11? So let's run through and see what factors of 12 we have. So I know I can do 1 and 12, 2 and 6, 3 and 4, and I think that is comprehensive. I think that gives us a whole list. So there's not any of those that would, where both of them would be the same sign to end up with a positive product, and they would both end up giving me a negative 11, because both of these would have to be a negative. So what that tells me is that the hopscotch square does not work. And what we said when we first started doing the hopscotch squares, if the hopscotch square doesn't work, that the polynomial was prime. But if there's a GCF, the polynomial is not considered to be prime. So we were able to factor out a polynomial, or factor out a GCF, and the polynomial part that's left over does not factor, which means this guy would actually be my final answer. That's as far as this problem could go. I would like for you guys to figure out, number 2, what's the GCF? And then which method would you use to factor the remaining part? So we have m to the 5th minus 81m. Hopefully you've been able to identify that the GCF for this one would be m. So we could divide that out from both, which leaves me m to the 4th minus 81. And then we take a look. There are only two terms left. So again, back over here, if there's only two terms, the only options we have for two terms are difference of squares, sum of cubes, difference of cubes. Well, this is definitely a difference. Is it a difference of cubes, a difference of squares, or none of the above? So with this one, this would be a difference of squares because both of these are perfect squares. M squared times m squared gives me m to the fourth. 9 times 9 gives me 81. So this would be a difference of squares. So we bring our GCF m straight down, and then we do our two sets of parentheses for our difference of squares, where we're going to try to see here, m to the fourth would be m squared times m squared. You're doing the square root. And the square root of 81, or what number times itself gives you 81, would be 9 here and here. You put a plus sign in one and a minus sign in the other. Now, with these higher polynomial degrees, like what we have here, we've gone through and done the work to factor, but then we have to look to see, does it factor further? Okay, does it factor any more or does it factor further? Well, m is m is m. We can't break m down any further. And then we have this little binomial, m squared plus 9. It's another binomial. So we have to look to see, is that binomial a sum of cubes, a difference of cubes, or a difference of squares? Well, it's a sum. So the only option we have is sum of cubes. M squared is not a perfect cube. So this will not factor down any further. But then let's take a look at this guy. M squared minus 9. Is it a sum of cubes, difference of cubes, difference of squares, or none of the above? Well, because it's a difference, it would either be a difference of squares or a difference of cubes. So are these perfect squares? Are these perfect cubes? This is a perfect square, and this is a perfect square. So we bring our m straight down. We bring our m squared plus 9 straight down because it will not factor further. And then we have this guy, which is another difference of squares. So this is difference of squares again. Okay, and this time we're taking the square root of m squared, which is m. We're taking the square root of 9, which is 3. We'll put a plus in one, a minus in the other, and now we check to see would either one of these break down further. We've already checked these two, and they do not. M plus 3. Is m plus 3 a sum of cubes, difference of cubes, difference of squares, or neither? Okay, that one would be neither. Here, m minus 3, sum of cubes, difference of cubes, difference of squares, neither, or none of the above, right? This one would also be none of the above. So this is your final completed factored form for this one. So again, the way that we started off this problem was asking, is there a GCF? There is one here. And then from there, how are we going to factor? And we factored by difference of squares. So it's kind of what I'm looking for, and we're not going to go through and do all of these problems, but I just want you to be able to recognize, is there a GCF? And then which method are you going to use after you pull out the GCF to help you factor the rest? Is there a GCF? If there is, go ahead and pull it out. And then is there, which method would you use to factor? Okay, you do not have to go through and completely factor each one. Just which method are you thinking that would be the best to use for that polynomial? Come back and check, and then we'll work a couple more together. Okay, so I've gone through on each one of these and determined if there was or was not a GCF, and then just written out which method I would want to use for each one of these. So it looks like we have quite a few that would be grouping, 1, 2, 3, these three. These two did have a GCF. This one did not, so I will go through and work one of those problems. And then over here we have a sum of cubes. We have a difference of squares, which we've already kind of done one like that. And then we have a 3-term where we would use either the box or grouping. So I think I'm going to go through and work just a couple of these problems just to help you guys out, getting a little bit more experience with these before we move on. So I'll do number 3, number 5, and number 6. So for problem number 3, we do not have a GCF, and then I identified this as sum of cubes. So remember, sum of cubes formula means that we have a perfect cube, we have a perfect cube, and then there's a plus in between them. So that's sum of cubes. All right, our sum of cubes formula, we had a cubed plus b cubed. Those are the two terms, right? And those will factor out to a plus b, and then a squared minus ab plus b squared. That's the pattern or the formula that we will always be following. So if we have 27a cubed plus 8b cubed, we need to figure out what is my a and what is my b. In other words, the cubed root of 27a cubed and the cubed root of 8b cubed. So 27 would be 3 times 3 times 3. A cubed would be a times a times a. So my a value in this case would be 3a, because 3a times 3a times 3a is 27a cubed. Okay, for my b cubed, what number times itself gives me 8. That would be a 2. And then b cubed would be b times b times b. Okay, so don't let the variables confuse you. The a equals and the b equals are the a and the b in the formula here, okay? In this particular problem, they also used a's and b's for the polynomial itself. So basically, whatever I have here, I'm going to put in place of this in this formula here. So for this problem, my a value, a is 3a, so everywhere there's an a, I'm putting 3a. So 3a. Okay, there's an a, so I'm going to put 3a in parentheses, and then it's going to be squared, and then minus, and there's another a, so I'm going to put 3a again. Okay, everywhere there's a b, I'm putting 2b, so we're going to put plus 2b, and then here there's another b, so I'm going to put in 2b, and then plus, I didn't leave myself quite enough room, so I'll put in another 2b, this time in parentheses, and squared. So the last thing you will need to do anytime you have the sum and difference of cubes formulas, it's to clean up the stuff over here in the parentheses. So we'll have 3a plus 2b. That's what I had right here. There's nothing I can do with that or simplify it or anything like that. Here we have 3a squared, so that's 3a times 3a, which is 9a squared, minus, here we have 3a times 2b, which would be 6ab, plus 2b squared would be 2b times 2b, so 4b squared. And that would be your final answer for this one as a sum of cubes. For number 5, we identified there was not a GCF, and because there are 3 terms this time, we could either use the box or use the grouping method. Since we're going to group over here, I'm going to go ahead and do the box for this one. So in either case, remember we do have to start off with the hopscotch squares. So the top box is the product, so y to the 4th times negative 48, so negative 48 y to the 4th. And then my sum is my bottom box, negative 13 y squared. Okay, so y squared plus y squared would give me y squared. So I know I'm going to have y squareds in there. And y squared times y squared would give me y to the 4th. So now I just want to focus on the negative 48 and the 13. So factors of negative 48 that would have a difference of negative 13. Let's go through and list our factors. We have 1 and 48, 2 and 24, 3 and 16. Ooh, I think that one's going to do it for us. So if I do a 3 and a 16, but in order to get a negative product, one of these has to be negative. and which one so that I get a negative 13y squared. So we would want to make the 16 negative. Okay, so now we create our box. First term goes in the first box, y to the fourth. The last term will go in the last box. And then these two guys we just found go in these other two boxes. Doesn't matter which one goes where, just one in one box and one in the other. And now across each row and each column, I need to determine the GCF of that one column. So across here, they have a y squared in common. Across here, it looks like they have a 3 in common. Going this way, they have a y squared in common. And going this way, they have a negative 16 in common. So what I end up with is y squared plus 3 and y squared minus 16. But again, like I spoke about one of the previous problems, when that exponent's a little bit higher, like a to the fourth, when we're going through and doing our factoring, we have to look to see, can this factor further? So anytime you end up with a non-linear factor as part of your answer, you need to check to see, can you factor that any further? So y squared plus 3, that is a binomial. Is that a sum of cubes, difference of squares, or none of the above? Okay, that one is none of the above, so it will not factor further. What about y squared minus 16? Sum of cubes, difference of squares, or none of the above? So that one is going to be a difference of squares because they are both perfect squares. So we're going to rewrite the y squared plus 3, and then we're going to factor out the y squared minus 16. So y squared would be y times y, so that's going to go in the front of the parentheses. The square root of 16 would be 4, so 4 times 4 gives me 16. Put a plus in one and a minus in the other. And that's it. So that would be your final answer, completely factored out for number 5. And last one of these examples for number 6, we are going to factor this one by group. When you group, remember we're going to bring that GCF straight down. And then I like to use a bracket here instead of parentheses just to differentiate with what I'm doing. We're going to group the first two together and the second two together. So here I have p cubed plus p, and we're looking for the GCF there, which will just be p, and leaves me p squared plus 1. Then we're looking for the GCF here. And if you're looking for a GCF, don't tell me there's nothing in common, because there's always a 1 in common. And in this case, there's actually a negative 1 in common. So we're going to factor out that negative 1, which would leave me p squared plus 1. We divide both of those by negative 1, and it turns that into a positive p squared and a positive 1. Remember, when you're factoring by grouping, these two guys should match. If they don't, either you've done something wrong or it won't factor by grouping. And most of your problems are going to factor by grouping right now. So then at this point, we're going to bring our GCF down one more time. And then we're going to take that factor, p squared plus 1, and pull it out from here. And then we're going to write down what's left over, which is p minus 1. So I see that I have a nonlinear factor because it's not p to the first power. Anything other than p to the first power is nonlinear. So we have p squared plus 1. Is that a sum of cubes, difference of squares, or none of the above? This one should be none of the above. So that tells me that it is factored completely. I cannot go any further. This is my final answer. The second page has some application of this whole polynomial factoring stuff that we've been working on. So the factor theorem is a really good tool to help us later on as you guys are graphing polynomials. So to be able to identify if a factor is a factor of a polynomial, so say a binomial is a factor of a polynomial f of x has the factor x minus k if and only if f of k equals 0. That's a lot of math words for not very much information. So x minus k would be whatever factor it is you're dividing by. So if I do x minus k equals 0, then that means x would have to equal k. All right, so it's saying when x is some k value, if I plug that k value in right here, that would mean x and k are the same thing. So if f of x equals 0, then that means this guy's a factor. Okay, still not making a whole lot of sense, right? Basically, this is saying that when you evaluate at a given value, a remainder of 0 means the binomial is a factor. Okay, basically if you're going through and evaluating and you get a remainder of 0, that just means that whatever you were dividing by goes in evenly. So I'm going to show you guys two different ways of thinking about these kind of problems. So we have determined whether the binomial is a factor. So this is the binomial, and we want to know if it's a factor of this guy. Okay, so the way that I'm going to start this problem off, there's two different ways you can work these problems. Okay, but I'm going to show you which way that I'm going to tell you probably want to do it. So the first way is we could just go through and factor this bad boy, right? It's a 4-term polynomial. We're pretty good at grouping by this time, and with it being 4 terms, we could just go through and group. And let's see if this ends up being one of the factors when we go through and group. Okay, so here and here, group those two together. All right, let's see, my GCF here is x squared, and that leaves me with an x minus 5. Cool. My GCF here, it looks like they have a 9 in common, but because the first one is negative, we're also going to factor out a negative. So negative 9, and that would leave me with x minus 5. All right, again, grouping. These guys should match. And look at that, they do. So we're going to pull that out, x minus 5. And then what's left is x squared minus 9. Now, if you stopped right here, this is not one of the factors we got down here. But based off of some of the stuff we just got through practicing, you have to ask yourself, will these go any further? Well, this one is linear. This is a linear factor, so it cannot factor any further. But what about this guy? It's another binomial. And remember, our options for binomials is sum of cubes, difference of squares. Is that going to be any of those? Yeah, this is actually a difference of squares. So because it's a difference of squares, it'll factor out one more time. So x minus 5, and remember our difference of squares will be 2 sets of parentheses. What's the square root of x squared, or what times itself gives me x squared? It should be x. And then here, the square root of 9 is 3. Put a plus in one and a minus in the other. Hey, look what I see. X minus 3. That's what it was asking about. So it says determine whether the binomial is a factor. Well, this is what we factored that polynomial out to. And x minus 3 was one of the factors. So our answer here is yes, it is a factor. Awesome. So that's one method, right? We could go through and factor and just see if what they gave me is one of the factors. Now let's give this one a shot. Oh, holy cow, those look huge, right? So still 4 terms, and we can still factor by grouping. I'm going to save us just a little bit of time. This one actually does not factor by grouping. So here's your second method, and the method I'm going to tell you guys you probably want to use, because most of the time when they're doing problems like this, it's not going to factor, which means you're going to need to just go ahead and take this binomial, whatever it is, and we're going to do synthetic evaluation. Yes, back to synthetic division and evaluation. So we take this guy, we set it equal to 0, and we solve it for x. So x equals a negative 7. That is what we use in our synthetic evaluation. And then remember what I said up here is we want the remainder to be 0. So all we're looking for down here is, are we going to get a 0 right here? Okay, so remember in synthetic division and synthetic evaluation, you always divide by what x equals. So x equals negative 7, so that's what I'm going to put right there. Okay. One of the big places where we continue to make a mistake is forgetting our placeholders. So take a look here, 3, 2, 1, and then constant. So we do not need any placeholders for this one. We're good. We'll just grab our coefficients. And start on our way with synthetic evaluation or synthetic division. Synthetic division, you just use the whole quotient. Synthetic evaluation, we're only looking for this value down here. That's the only difference. The process is exactly the same. So we're going to bring down the 3. And then to start the process off, we multiply to the corner. So 3 times negative 7 is negative 21. Negative 21 and negative 28, we're going to add those two together. So that's going to give me a negative 49. All right, we're multiplying that negative 49 times 7. And a negative times a negative is a positive, and so that would give me a positive 343. Okay, we're adding going down, so that'll give me 372. We're multiplying to the corner. These are some gigantic numbers, so I get negative 2604. And then we add going down, and I get negative 2464. So because our remainder is not 0, in fact, it is way not 0, this would be no, x plus 7 is not a factor. Okay, so again, this is my suggested method to go about doing these problems when it's asking you, is it or is it not a factor, is to go through and do your synthetic division. Okay, if it'll factor, great. And if you're a fan of factoring, that's totally fine. But I'm going to say that a lot of problems you're going to run into are probably not going to factor, so you're going to want to do the synthetic division instead. Okay, so when it says determine whether the binomial is a factor, it's basically just a yes or no. So because the remainder is not 0, x plus 7 is not a factor, right? If the remainder is anything other than 0, the binomial given will not be a factor. I would highly recommend that you guys do this method versus trying to factor. Sometimes because the factoring won't work, it actually will not factor, like this one. This one does not factor by grouping. So then we have to take a look at doing it by synthetic. So I think this is probably an easier and faster way to do it anyway. That's my suggestion there. Okay? The last 3 problems of the notes today are going to be about showing that the binomial is a factor of the polynomial. When it asks you to show that the binomial, they're trying to prove or verify that it is actually a factor. So when that happens, what we have to do is figure out, does this have a remainder when I go to plug it in? So when it says show, we're just looking for, is that remainder equal to 0? So we're going to do the same thing on these 3 problems that we did on the last problems, where we're going to use our synthetic division, and we're basically just looking, do we have a remainder of 0? Now, I will tell you, when it says show that the binomial is a factor, most of the time, it's going to give you a binomial that actually is a factor. So we should be coming up with a remainder of 0. All you need to do is show that the remainder is 0. So again, remember, you're going to take your binomial, set it equal to 0, so x would actually equal negative 1, and that's what I'm going to use for my divisor over here is negative 1. Don't forget, we have to have our placeholders. So on this one, we have an x to the 3rd, and then we go down to an x. So in here, we need that placeholder of 0x squared. So we use our coefficients. We'd have 1, then a 0, then a negative 13, and a negative 12. We're going to bring that 1 straight down. 1 times negative 1 is negative 1. Add these guys going down for negative 1. Negative 1 times negative 1 is positive 1. Add going down, so we get negative 12. Negative 12 times negative 1 is positive 12. And when we add going down there, we do get a remainder of 0. So because the remainder is 0, x plus 1 is a factor of this polynomial right here. The second part of the instructions are probably the ones that are going to require a little bit more work. Then we need to factor the function completely. So what we're doing here is completely breaking it down. You remember the factor tree we did at the very beginning? Yeah, so we're basically doing a factor tree for this polynomial, for the whole thing. So we know, I'm actually going to scoot down here to give myself a little bit more room. We know that x to the third minus 13x minus 12 is equal to x plus 1 that we just figured out was a factor times the quotient we have right here. Now let's add those variables back into our quotient. So this is our remainder, this is our constant, which means that this guy would be x, and then this guy would be x squared. So then down here we would have x squared minus x minus 12. Okay, so basically what we just did is we divided out x plus 1 from x to the third minus 13x minus 12 and realized that what's left is x squared minus x minus 12. Okay, so when it's saying to factor the function completely, we've factored it a little bit because we pulled out the x plus 1. But now we have to take a look at what's left over here. And again, because what's left over is not a linear term, we know that it could possibly factor again or factor down further, and this one does. So we're going to take that x plus 1 and rewrite it. And then x squared minus x minus 12. I'm actually going to do this one without the puzzle. So we're going to talk through that real fast. So I know x squared would be x times x. All right, and it's pretty easy when your coefficient here is a 1, your leading coefficient's 1. So all we have to look at is the negative 12. So we're asking factors of negative 12 that have a difference of 1. So thinking about your factors of 12 that have a difference of 1, which would be 3 and 4. And now it needs to be a negative 1 so that when I add the 4 and the 3 together, I'm going to end up with a negative 1. So I'm going to say a negative 4 and a positive 3. If that overwhelms you, that's not a problem. You're welcome to go ahead and do the hopscotch squares in the box method or the grouping method like we've been doing. But for those of you guys that are starting to catch on to what we have going on with the factoring trinomials, this is how you can factor the trinomial without using either one of those two methods. Okay? So show that the binomial is a factor of the polynomial. That's what we did here by getting a remainder of 0. And then we factored the function completely. And that's, so again, our directions are to show that the binomial is a factor. So we're going to show that this is a factor. We set it equal to 0, x equals 2. So we're going to do our synthetic division. Put the 2 here. Check for placeholders. So we have 3, 2, 1, 0. Don't need any placeholders, so we're using our coefficients 6, 8, negative 34, and negative 12. First number is a 6, comes straight down. 6 times 2 is 12. Add these. 8 and 12 gives me 20. 20 times 2 is 40. We're going to add those together. Negative 34 and 40 gives me 6. 6 times 2 is 12. Negative 12 and 12 gives me 0. So because the remainder on this one is 0, we know that x minus 2 is a factor of the function here. So this function f of x, if we were to divide it up, would end up being x minus 2 times our quotient that is right here. So let's add our variables back into our quotient. We have a remainder, which means this is a constant, which means this would be x, and then this would be x squared. So we know that our divisor, x minus 2, times our quotient, 6x squared, plus 20x plus 6, if I was to multiply those back together, would get me back to this f of x function, the 6x cubed function up here. Remember, the second part of our directions are to factor completely. So this is a linear polynomial, so it does not factor anymore. But then we take a look at this guy here. All right, what I recognize on that one, remember when you're factoring, the first thing you have to look for is there a GCF? I know we haven't run across this in any of our other problems, but this one does have a GCF kind of as we're in the middle of the problem. So we're going to pull out the x minus 2. All of these are divisible by 2. So I'm going to go ahead and pull out a GCF of 2, and that's going to leave me with 3x squared plus 10x plus 3. And then we're going to have to factor this guy. All right? With there being 3 terms, we're factoring either by grouping or by the box method, but in either case, we're going to use our hopscotch squares. So let's go ahead and do our hopscotch squares. Okay, again, I'm only focused on this trinomial. The rest of this, we're just rewriting until we're done. All right, so our product is the first times the last, so 9x squared. The middle term is the bottom, that's our sum. So we're looking for factors of 9 that add up to 10. And the only option there would be 9x and 1x. 9x times 1x would be 9x squared. 9x plus 1x would be 10x. So that means only for this part right here, that middle term, 3x squared, the middle term we're going to break up into a 9x and a 1x. Okay, I rewrite my x plus 2. I rewrite my GCF of 2. Now we have to do our grouping. So now we're going to take this guy and group these two, and group these two. Again, I'm rewriting all of this. So we have x minus 2. We have a 2. Now we're looking for the GCF here. So I'm going to do a big set of brackets here because that's going to hopefully indicate to you guys that we're doing grouping here. All right, so the GCF in this group right here would be 3x, which would leave me with an x plus 3. All right, the GCF between these two, remember there's always at least a 1 in common. So our GCF in this case would be positive 1, which would leave me with an x plus 3. All right, one more time. Rewrite the x minus 2. Rewrite the 2. Remember when you're grouping, this guy's got to match this guy, and they do. So we're going to write that down, x plus 3. So from my brackets here, after I take out the x plus 3, what is left is 3x plus 1. One more example, similar concept. So I just kind of want to continue to work and make sure that you guys are good with these problems. So again, x minus 5 equals 0, so x would equal 5. So our divisor is 5 on our synthetic division problem. Okay, look for placeholders. So we have 4, 3, 2, 1. There's not a constant of 0, so we're going to put plus 0 back here at the back, just in case. Then pull your coefficients, 2, negative 12, 6, 20, and 0. All right, pull that first one straight down. 2 times 5 is 10. Add these guys up. We have negative 2. Negative 2 times 5 is negative 10. 6 and negative 10 is negative 4. Negative 4 and 5 is negative 20. Negative 20 and positive 20 is 0. 0 times 5 is 0. 0 plus 0 is 0, so our remainder is 0. Now the nice thing about putting your placeholders in on this one is that your exponents are not going to get off when you're adding in your variables. So this is a remainder. This would be your constant of 0. So this would be your x squared, and your x to the third. So again, for this problem, we have shown that x minus 5 is a factor because we got a remainder of 0. So we know that x minus 5 times 2x cubed minus 2x squared minus 4x, if I was to multiply those back together, would equal this f of x function we have here. So now we need to completely factor, which means then take a look at this guy right here. X minus 5 is linear because it's x to the first power, so that one's not going anywhere. Then we have this guy right here. So the first thing I look for when I'm factoring is a GCF. This one does have a GCF. So I'm going to rewrite my x minus 5. And the GCF in this case would be 2x. So pull out that 2x. And then what that leaves me with, if I divide out all three of these terms, if I divide all of them by 2x, 2x cubed divided by 2x is x squared. Negative 2x squared divided by 2x is negative x. And negative 4x divided by negative 2, or by 2x is negative 2. So then we ask, can this factor any further? And yes, it can. So I'm going to bring down my x minus 5. I'm going to bring down my 2x. And then this guy we're going to factor. You can use your hopscotch squares and use your grouping or your box. I'm going to do this one without either one of those. So because the coefficient here is a 1, I know that x times x would give me x squared. Then we're looking for factors of 2 that have a difference of 1. So that would be 2 and a 1. And because this is negative, we know the signs have to be opposite. And in order for these guys to add up to the negative 1 in the middle, this would be a negative, this would be our positive. So this guy would be your fully factored version of your original f of x function we had here. Okay, so the big idea on these is making sure you understand what the directions are asking you for each one of these problems. So again, just to go back and double check, it says determine whether the binomial is a factor. Determine would be a yes or no. Determine whether you're going to go to a movie on Friday. That's a yes or a no, right? So that's where you're going to go through and look to see, do you have a remainder of 0, or when you factor it out, is it actually a factor? Versus the instructions down here say show that it is a factor of the polynomial. That means you've got to show me that the remainder is 0. Show that it actually shows up as a factor when you go through and do the work. So a little difference in the directions there, just make sure you understand the difference between the two. Other than that, hopefully all of this made sense. You guys let me know what questions you have.